So to kick us off will be our discussant, Yu-Chen, who actually also gave a talk somewhat recently. So take it away, Yu-Chen, and then afterwards, Sander, you can dive right into it.
Cool. So let me first quickly recap that causal abstraction considers the case where we have a ground truth causal model over some fine-grained variables. And we're interested in defining causal models among macro variables, which arise as functions of subsets of the fine-grained variables. For example, you can consider a neural network as a giant fine-grained causal model, but you want to understand what it does in terms of some high-level concepts. Recall that in the first talk of the series, I showed causal abstraction from the point of view of micro-level implementations. I illustrated the consequence that choosing different micro-level implementations can make certain structural properties of the macro causal model, namely confounding, ill-defined. Earlier works take a different view, where they first hypothesize some fixed causal model over the macro variables, and then they check if it is consistent with the micro model under observation and interventional distributions. And then we have Atticus Geiger's talk, which applies this view, this macro model first idea, if you like, for neural network interpretation. First, we need to come up with some hypotheses for what the neural network is doing over some macro variables, and then we check if it is consistent with the low-level model over all interventions. Here, an intervention is given by an input data point, and Atticus generalized the notion of interventions to interchange interventions for this purpose. And now for today's talk, we're going back to the implementation first view. Sander will introduce a new machinery called generalized functions, which are functions that output sets rather than points. A generalized function arises from maintaining uncertainty over some input variables or mechanisms of a causal function. A macro causal model may arise as a collection of generalized functions in the sense that a state of a macro variable can be first mapped to a collection of microstates. Run the micro causal model on this collection to obtain the effect states, and then map the effect states back to the high level. So Sander will also describe some examples, I believe, of abstractions, which can be described using generalized functions. So on this note, I'm happy to hand you over to Sander, who will tell us more.
Thanks a lot, Yu-Chen, and especially for preparing all of this without having an actual paper to read. And so that wasn't an easy task, I can imagine. Is my screen being shared now? And are you viewing the...
Good.
Yes?
Yeah.
Good. Oh, I hate this now. I don't see anything anymore. How can I only see my screen. I don't know whether people are still there or not. I'm not sure if I can change that, but yeah, so now I definitely can't see if anybody's asking anything or not. All I see is my screen. So you'll have to shout out if you have a question.
Perfect.
Okay, I feel on the one hand that I'm underprepared, and on the other hand, I feel overprepared. I'm underprepared because this is very much still work in progress, and so not all of these ideas are fully precise and worked out. I'm overprepared because I've got way too many slides and way too many things to explain to you in 45 minutes of time, so I'll just get started quickly. And I'll go a bit in reverse order, because rather than diving into the technical details, I might lose some of you because you might wonder, why are we doing all this? So I'll start with just giving you a bit of a perspective of what motivates connecting this work that I've been doing with abstractions, because the idea of generalized functions was actually not initially only about abstractions. It was a more general approach. So what motivates this new work? And I tell you a little bit about what we could do with it, and then I only explain how we make that precise. So reversing a bit the order, so that if you don't like the motivation or at least don't have enough time, you can at least already get the sense of what I'm trying to do, and maybe then zoom out for actually me working through how this all works. And eventually then hopefully read the paper if it at some point is realized. So my literature, knowledge of the literature is actually very restricted in the sense that the only 3 papers I can confidently say I've read really clearly are these 3. And I know lots of interesting stuff has happened afterwards, and I know some of it, but not as closely as I should, because I haven't been thinking about abstractions for a long time myself either. So I'm now getting back into it. So there may be things that I'm saying which are related to things that people have been doing that I'm not acknowledging properly, and sorry for that. But this is going to be my starting point. So I'm going to present what I took to be the perspective on abstractions in those 3 papers, and also how it was seen by many people. And I'll try to then move towards how we can see it in a new way by using generalized functions, and try to motivate why that's a sensible thing to do, why to shift from the old perspective to the new. So I'm going to go very quickly through this because, well, at least here's an audience where I can assume that you're somewhat familiar with this. But I have to explain the notation I'm using and what kind of causal models I'm talking about. And if you're familiar with my papers in abstraction, then you should be familiar with the fact that I'm using Halpern's notation, which is very logic-based. So we have a signature, which is telling you what the exogenous variables are, U. It tells you what the endogenous variables are, V. And then there's also R, which is giving you the range of all the values. And the notation is always with vectors. So vector X refers to a tuple of variables, and then if we take the range of that, it's essentially the Cartesian product of each of the ranges of the variables separately. That's the signature. Now, what makes a causal model is, of course, the equations. So these are deterministic, right? Causal models, the standard structural equation view. I'm not going to be talking at all about probabilities or causal Bayesian networks, although there are going to be interesting connections to those, which I'll be silent about because there's too much, there's only so much I can say. So a structural equation, F, and we need one for each endogenous variable, right? And the cleanest way to do that is to say that the equation takes the form X equals, and then some function, which is distinctive for X, so F subscript X, and the arguments for that function, so the domain, is all of the other endogenous variables and all of the exogenous variables. Now, of course, in practice, not all of these variables might matter for determining X. So in practice, what we usually do is we restrict the function X for X to its parents, what's then being, how we speak about it. And the parents are precisely those variables which actually matter. But to make it clean as possible, you should actually say it's a function over all the other variables. Now, these are all common aspects of a causal model. What Rubinstein et al. Introduced in their original paper on exact transformations or abstractions, however you want to call it, is that there's also a set of allowed interventions, because we don't want to consider all the possible interventions for several reasons. The most important one, some of the interventions at a lower level might not have any counterpart on the higher level, and therefore we're not going to allow those. So a very simple example, imagine that you have low-level variables x1 and x2, and we're somehow going to abstract these to a new variable a, and where a is simply the sum of x1 and x2. If we're then considering intervention on just x1, how could we possibly represent that at the high level? It's not well defined. So because of that, we don't want to consider that intervention at all. And we can be more, even more open-minded by just explicitly stating what a set of allowed interventions are, both at the low level and at the higher level. Now, obviously, probabilities matter. What is kind of Halpern's way of adding probabilities? You just take a deterministic model, but then you add the probabilities over the exogenous variables. And this then induces probabilities over the endogenous variables. And that's of practical importance, but I'm not going to focus on that today at all. Okay, so what is the idea of an abstraction? Assume we have somehow a low-level model, ML, and a high-level model, MH, each with their respective signatures, and we have some surjective function tau, which goes from the values of the low-level endogenous variables to the values of the high-level endogenous variables. That's given. Now, the problem is how can we extend the interpretation of this function tau so that we can somehow apply it to the entire causal model, not just to the values in endogenous variables, but to the entire model? How can we make that precise? What would that mean? And the way we go about that is by saying, well, a causal model can itself be viewed as a function. You give it a setting for the exogenous variables, which is called a context. Then you also specify which intervention you're going to consider. And then it tells you what the values are for the endogenous variables. So it's a function taking both contexts and an intervention mapping to values for the endogenous variables. So if you want to now apply this tau function to the function for the causal model, we somehow need to be able to make sense of tau of the separate elements. So we already have that tau takes care of the endogenous variables. We need somehow to extend it so that there's also a tau associated with the exogenous variables. So that's going to be tau UL. And we need to make sense of the interventions being mapped. And for that, we have the function omega tau, which is going to tell you which low-level intervention maps to a high-level intervention. And if you've done that, then you can express what it means that a high-level model is a low-level, is a tau abstraction, sorry, of a low-level model. Namely, there's a universal quantifier over all the possible low-level contexts and all the possible or allowed low-level interventions, such that if you fill in those values into the low-level function, that gives you a solution for the low-level endogenous variables. You then apply tau to that solution, and you arrive at a certain high-level point. If you were now to try to arrive at the high level by a different route, namely, you first map the exogenous variables to the high level using tau of UL, and then you map the intervention to the high level by using our omega. Then you arrive at a high-level intervention, high-level context. You plug that into the high-level causal model, and you arrive at a point, and that point should be the same point as you initially arrived at. And if that is the case, then we have an abstraction. Okay, so this is really building on or invoking the idea that the causal model is a function, but it didn't do so in a very precise way. And there were several technical challenges to make all of this work. And the things in blue are things which I can offer by the new work that I'm going to present, which weren't really there in the previous perspective. So even though we're speaking of this causal model as a function, how does it really relate to the actual functions which appear in the equations that make up the causal model? In this new perspective, that relation is going to be entirely clear. Then these additional functions that we required for the exogenous variables, for the interventions. Well, first of all, we never focused too much on the exogenous variables initially. Now it seems more sensible to just have one tau, which maps from exogenous and endogenous variables together to the high level, because you might want to allow mixing. In particular, what you might want to allow is that some exogenous variables are marginalized away. That wasn't possible previously because that would introduce non-determinism. And I'm getting ahead of myself, but we'll see why that becomes possible in the new perspective. So we just have one tau function. And then also this idea of omega, we try to make it precise by saying, okay, you can't make sense of all the interventions. There's a cleaner way of doing that in a new perspective. And for that, it's cleaner because it will be able to make sense of applying tau to any intervention, any tuple. And also be able to make sense of the inverse of tau. So these things were not standardly possible. Okay. All of these things, hopefully you'll see how they can be delivered when I show you what the new perspective is, but there's more important aspects to consider. First, I should make clear, sorry, somebody was asking something.
Yeah, it's me, Danya. Can I ask a quick question about the motivation for technical challenge 1?
Yes.
Could you say a bit more about what you mean when you say, how does the functional view of a SCM relate to the actual functions? Just because it seems like it's pretty clear, right? Like you would recursively apply the functions of the SCM, and that's how the functional view of M relates to the individual Fs that make up M. I'm kind of wondering what is the remaining mystery?
Well, if you strictly speaking, if you want to consider M as a function, for example, what is its domain? Because you might have a fixed range and a fixed tuple, namely all the exogenous variables, but the interventions, they vary, right? You can intervene on one variable, on two variables. So already we're already being very open-minded as to what we mean with a function because we're varying the domain. So it might be clear that that's very well the case, but I'm going to make it clear anyway, and then that opens up the door to really taking very literally the idea that a causal model is a function. But I'm not going to say it's groundbreaking. I'd say quite the contrary. I hope it's quite a kind of commonsensical, and therefore all the more acceptable to everyone. I still believe it that even though it's commonsensical, it will have many benefits. But we'll get there at some point, and then you can see whether that you agree or not. To be clear, for the moment, I'm restricting myself to constructive abstractions, although I do think there's ways of generalizing in the future, but to make things easy, I'm going to focus on a particular kind of abstraction, which means that tau has a very nice form. So the function tau essentially clusters low-level variables, and each cluster is mapped to a single high-level variable, and the clusters don't overlap, right? So for each high-level variable yi, there will be a specific function tau I and specific low-level variables zi, and so that they're all nicely separated, partitioned from each other. So I have a picture that I stole from another paper because, like I said, I don't have good graphical skills, certainly not when I was preparing this talk and I had too much to do. So this visualizes the idea. On the bottom, you have the low-level variables, and each color here indicates a cluster, meaning that each color will represent one variable at the high level. So the U high-level variable is actually an abstraction of the three variables on the three brownish variables on the bottom, and similarly for Y and Q. And so we have separate functions tau for each of those, and the full tau is simply the composition of those separate functions tau. And that might make life easy, in particular if we're going to invert tau. It's very clear what it means to invert tau in this case, and it's not so clear if the function is more complicated. Okay, this was all about the past. Let me move to the future. So just assume from now on that we just have a low-level signature, high-level signature. We have some constructive function tau. Also, for now, I'm going to restrict myself to acyclic causal models, and it will become clear why I'm doing so in a second, or at least in a bit later. I hope to generalize later to cyclic case. First, I'm going to show, or not show, I'm just going to tell you that you can actually define abstractions equivalently by starting with the high level. So recall that what I told you earlier was we have universal quantification over all the low-level intervention context pairs. Well, you could also formulate it at the high level, and that makes life easier. So you start with a high-level intervention Y, a high-level intervention, context UH, and then you can say, okay, now apply the high-level causal model. You'll end up at a point, but you could also say, let's move down to the low level. So we apply the inverse of tau, and then we move through the low level, and then we afterwards apply tau again and see where we end up. Now, of course, if you're going to do the inverse of tau, you're going to have a lot of possibilities. So it's no longer going to be a single value. But still, if it's an abstraction, you can show that it should still work because it shouldn't matter which low-level realization you've chosen. They should all end up in the same point. That's the point, that's the property of an abstraction. So a theorem, which shouldn't be too hard, is that you can reformulate the idea as follows. It shouldn't be too hard, except that I haven't explained to you yet what this notation FH and FM means. But intuitively, I hope you can get the picture. So we simply demand that for each high-level intervention and each high-level context UH, the high-level causal model, so that's FHM, it behaves in the same way as simply going down by the abstraction function to the low level, so then pushing through the values through the low-level causal model and then going up again. And so we can write this simply as an equality between two functions. We have our high-level function, FHM, and we have then this composition of the low-level causal model with tau and its inverse. Now, of course, to make this precise, I need to give you a story as to what it means to represent these causal models as functions, and they're going to be generalized functions. So their domains and codomains, they're not going to be fixed. And because of that, each of these functions is actually a family of functions, because the domain is going to tell you what function in particular, what instantiation of this function are we looking at. Also, how do they relate to the functions that appear in the equations? Well, they are literally constructed out of those functions. So I'm just going to give you a construction for this idea that a causal model is in fact nothing but a function by making it very explicit how the functions in the equations can be composed together to give you a function for the full causal model. And if I've made that precise, which I'll do later, then we have now this equivalent description of abstraction for deterministic causal models. So the causal model that I've introduced, but then we can take that result and use that as our definition for abstractions in the non-deterministic case as well, which is going to be a generalization. Right? So one crucial aspect is I will be generalizing causal models to non-deterministic causal models. And we can take the result as a definition. And crucially, we can actually use this to then immediately construct a high-level abstraction, which I'm going to call the canonical abstraction. So if you just give me a low-level causal model, M, and I have the signatures, like the low-level signature, I have the high-level signature, and I have my function tau, then I can immediately tell you what the equation is going to be at the high level for each high-level variable. Namely, I'm going to take the function that represented the entire high level, FHM, and all I'm going to do is I'm going to restrict the domain so that it fits with the domain that you would expect the equation for VH to have. Namely, the domain consists of all the high-level exogenous variables and all the high-level endogenous variables except for VH. Simply by specifying that that's the domain, this function, high-level FHM, is going to behave in the right manner. Now, this is all going to rely on the fact that FM is acyclic. Now, this canonical abstraction, if you're just leaving it open what tau is, it might be that the high level that you get as a result is not going to be acyclic, and therefore it might, strictly speaking, not be an abstraction because I've defined abstraction only for the acyclic case. So for now, that's a limitation. And yeah, in future work, I'd like to generalize, but you'll see why the acyclicity comes in a second. Okay, why bother with all this, right? What's the point? Well, there's certain properties that this will allow for. So we don't need to consider an explicit set of allowed interventions. We can construct a high-level model directly. Also, we can marginalize away exogenous variables, which is something that couldn't be done previously. Now, of course, doing so will create non-determinism. And in fact, it might possibly violate causal sufficiency, because if you have an exogenous variable, which is a common cause of two variables x and y, and you're marginalizing it away, then you don't know anymore that x and y were dependent. But there's even a more general point regarding non-determinism. By using abstractions in this manner, we can have that the high-level or the low-level model can be non-deterministic. And this means that we can have a lot more causal models such that the one is an abstraction of the other. So the scope of the abstraction relation becomes much broader by allowing for this non-determinism. And finally, we can define something that I will call strong reduction, which is a way of becoming agnostic regarding variables, which is stronger than marginalization is, which introduces even more non-determinism. I'll get to that later, I hope. Now, still, that's just an answer to what do we get out of this? And these are just some of the properties. You might still ask yourself, okay, sure, but why bother? Why would we need all these things? And this is not something I can give you a very strong or confident answer about. All I can do is hand wave a bit. Well, first of all, pretty from a mathematical point of view, if we can do it, why not? It's a good exercise. Let's see where it brings us. And I am confident that there will be interesting real-life applications. I just haven't looked for them yet. This is still work in progress. Now, I'm also a philosopher, and I'm definitely convinced that this will be useful for lots of debates in philosophy of science regarding different levels and whether some level emerges from another, and the debates regarding causal exclusion, etc. And if you want to see an example of what I mean, well, Woodward, who's arguably the most important philosopher of science talking about causation, has recently written a paper in which he makes use of all the technical developments within causal abstraction to make arguments regarding these philosophical issues. And I'd say that this new perspective allows even more contributions in that regard. For example, there's a case which many of you might be familiar with, this idea of cholesterol. So you have LDL and HDL, which are different forms of cholesterol, or at least things which are related to cholesterol. And they have, the one has a positive relation or a positive causal effect on your risk of heart disease, and the other one has a negative. Now, what if you only can measure the total cholesterol, which is a sum of these two various types of cholesterols? Then the idea is that interventions on that total cholesterol level will be ambiguous because they might be realized in different ways. And therefore, there's no, we shouldn't be allowed to somehow write an equation for heart disease just with total cholesterol as apparent, precisely because of this ambiguity. And indeed, that's a point that Woodward makes. Well, you can't allow this if you use everything that existed so far. You can allow it if you just make precise that there is this ambiguity. And this will be the case if you allow for non-deterministic causal models. So then nothing prevents you, at least, for considering a high-level model where you have total cholesterol as a parent of risk of heart disease. It'll just be that the causal model won't be specifically telling you what value for heart disease there's going to be for each intervention on total. It'll be ambiguous or non-determined. Okay, this is the part where I've hopefully somehow given you a sense of what all this is going to be about and why it might matter. I have not yet in any way made precise or fulfilled the promise of delivering any of these issues. And that's what I'm going to get into now. So this is where, oh, sorry, I wasn't finished yet with motivating the topic, but I'll quickly say that I think it also matters for causal representation learning, namely that it might be useful in many cases to abstract away to a higher level, even if it comes at the expense of non-determinism. Because sometimes it might be that all the causal dependencies that we're interested in, if they're still present at the high level, and some other relations might be non-deterministic, who cares? Like, it might be very useful to still say, let's go even further away, abstract even further, if we can get a much simpler model. And in fact, maybe non-determinism reflects our state of ignorance regarding the world, and maybe we want to capture that. In any case, this is very, very brief. You can also pause the slide, or if you're watching the recording, you can actually press pause and read the actual slide. I'm going to have to dive into the technical stuff now, because otherwise I'll never get anywhere close to being finished. So, okay, this entire project is built on the idea of a generalized function. And as such, I don't think that's a very innovative idea. I think it's quite straightforward, and I'd say that's a benefit. So what are generalized functions? What do I mean by that? Well, first, some notation I'm going to be using. So assume we have a signature, because all the functions that we're going to be considering are going to be from variables to variables. And we're just going to assume that our variables that we're going to be considering and all the ranges are coming from some signature S. And so therefore, all the x's that we're going to be having, there's going to be subsets of our variables. Minus x is going to be the complement of x. Low letters are going to be values of the high level, the capital letter variables that they correspond to, right? So little x means it's some value of capital X. And since x is a tuple, we might not be interested in all of the elements of it. If we want to restrict the values in x, little x, to those in the tuple y, I indicate that with a subscript y. So that's just going to be only the values of x that are appearing well, in the intersection of the tuple x and y. Okay. Now, to get the non-determinism in there, I'm going to be working with multi-valued functions. So that means that for each input, you get a set of outputs, right? So any value x, you'll be mapped to a set of values y. in this case, where y is just another tuple of variables. And by doing so, we can define what I call a generalized function, which means we can play around with the domain. So strictly speaking, the function f might be going from the values of the variables x, but we can interpret it as if it's not. So for any tuple z, I can still make sense of what it would mean to interpret the function z as if it, interpret the function f as if its domain were in fact the variables in z. How do I do that? Well, the equality on the bottom tells you that. So I'm going to consider all the values x and the outputs that they would give, and then I'm going to join them into one big set. And that's fine because I'm dealing with a multi-valued function, so it's no problem having multiple solutions. And which x's I'm going to consider? Well, all those x's, such that if I were to only look at the components in x which are also variables in z, then they agree with those components in z that I've given. So this sounds very abstract. I'll give you an example in a second. What I've just said was defined for general domains and codomains. A very interesting special case will be where the codomain consists of just one variable, right? Because those are going to be the functions that we're going to be using in our causal models. And for those functions, I'm going to define the idea of an extended function. Why? Because this allows us to compose functions after each other without losing the input that we gave it. So if we're going to recursively solve the equations of a causal model, we don't want to lose the input that we gave, and the extended function simply makes precise the idea that you're passing through the input as well. So we are using our generalized function idea. So we have our function f, but we can interpret it over any domain we want. And what is the extended function? Well, what we do is we look at the output that we get. So y might be one of the outputs, and then we just add it to z so that we just don't lose z either. So it'll return both our input and the output. Now, there's a crucial aspect here. Since I'm talking about variables, and each variable can only have one value, in at least in any given solution, right? For any given tuple, each variable will have one value. What if the variable y already occurs in z? Then we're going to have to choose, because then we have our value of y as it was given in the input, and then we have our value of y as it's determined by the function. Which one of those are we going to keep? Now, here I make the choice that we're going to keep the input. And this is because this aligns very nicely with the idea of an intervention. If I'm intervening, I don't care about the function anymore. And this will become precise in a second. But that's why in the statement on the right there, it mentions that we're going to restrict y to the complement of z. And that simply means if y is an element of the tuple z, then we ignore it. If it's not, we add it. That's what it comes down to. Sorry, but we're not finished yet. With these definitions, we can go even further, because the purpose of these extended functions was to allow defining compositions. So that's what we're going to do next. And first, there's already a preamble, and this is very straightforward. You can consider a function on a set of input values, and that's also a function, right? So then you have a function from a set to a set. So that's on the top, you see fa equals. If a is a set of values, then you just take the union of all the inputs, and that's going to be how you interpret that function. Okay, so with all this in place, we can now define a generalized composition, where again, the functions we're considering have as codomain just one variable, right? So imagine we have f, which goes from some tuple x1 to y1, to sets of y1. We have g, which goes from x2 to our tuples, to values of y2. The composition is just going to use this idea of an extended function. So it's just going to compose the extended function. So first we do g for any input z. That gives us both z and the output of g. So that's going to be a set of values for y2. And we're going to feed that into f and see what it returns. And that is the composition. And we can do the same for, of course, not just for two functions, for any finite amount of functions, you can keep doing that composing. So to be clear, if you have such a composition going from fk to f1, the domain of that function is determined by the arguments you're giving. So if you're giving it as an argument to tuple z, then those variables in z, those will be the domain. The codomain is going to be the power set of the union of the variables in this domain, so z, and all the codomains of the functions that you've passed through, right? So you're just going to always keep the input and output and just concatenate them to each other. Of course, taking into account that there will be many solutions, so you'll end up with a set of outcomes. Okay, now why do we bother going through all of this? Let me first illustrate so that you see how it works in practice. So a multi-valued function, that simply means that you might have multiple solutions. So if g of xy could take on the form that it gives you x plus y and x minus y. There's two solutions to the function, and therefore it's a set. Imagine that we have a function f which takes values for x, y and maps them to z, and the ranges of x and y are simply 0, 1, and 3, 2, and 3, and the function is simply the sum. What does it mean to then interpret the generalized function where we only consider a value for x? So I'm indicating that with 3 subscript x to indicate this is the variable x getting the value 3, and I've ignored y. Well, to solve that, you just take into account all the possible values for y and return all those answers. So since the range is 0, 1, and 2, and 3, if you give it x equals 3, then the outcome will simply be that z is going to be 3, 4, 5, or 6. Yeah, I hope the rest of this is clear. I'll just move on to the next. But again, those who are watching the recording, they can pause and look at the examples. But it should be straightforward, I hope. Now, why do we go through all this trouble? To make very precise that causal models simply are generalized functions. And how does that work? Well, the starting point is this idea of these multi-valued functions. We're going to take those for defining our equations. So a non-deterministic causal model is going to be exactly as before, except that the function in each equation is going to be a multi-valued function. And then we're going to do everything as we did for deterministic models. So we consider a context, which is a value for the exogenous variables. We consider state, which is a combination of a context and values for the endogenous variables. And then we want to look at solutions. So a solution of an equation simply means that you have a state such that if you look at the x component of that state, then that actually is part of the solution for the equation or the function of x, fx, when you fill in the rest of the state and that context, right? So Vx is an element of Fx when applied to V without X and U. That's for a single equation. A solution of the entire causal model is a state which is a solution of all the equations. So the only difference with the deterministic case is that we don't have a unique solution. We could have many solutions to the equations, even if we hold fixed the context. Now, I've spoken a lot about acyclicity. This is why. I'm going to assume that we have recursive models. And that means that there's a partial ordering such that we can actually order the variables in terms of their dependency relations. I haven't defined dependency here for sake of time, but it's very similar to it was in the deterministic case. So we have this idea of x being a parent of y, and then we want the order to reflect that. And if that's the case, we can actually index all the endogenous variables so that the indexes track the order, meaning that the lower indexes are higher up the causal graph. So that if we want to solve the equations, we start with the equations for the lowest indexed variables. And then we're certain that we're not going to be relying on any of the variables which are coming later. That's why we need recursivity. Given that we have this ordering and we've indexed the variables, we can now consider the composition of all the separate functions for the variables. And I'm going to call that Fm. That's going to be the causal model interpreted as a generalized function. So it's going to be the composition of Fn after, et cetera, after F1, where n to 1 are simply the indexes of all the endogenous variables. And you can actually then use this generalized function to capture all the solutions, right? A state is going to be a solution of the model. It will be precisely that it's going to be a solution also for the generalized function if you give it that particular context. But there's more. So we have the causal language. And in fact, all the expressions that you can get in the causal language can be captured by generalized functions. I'm not going to go through the details. That would take too much time. But I'll just go immediately to the results because you know how the causal language works, right? Again, this is helper and style notation, but for you must have seen variants of it. So you can express what happens in case you intervene on a certain variables, then a certain formula is going to be true. And instead of having single solutions, we might have multiple solutions. So we're going to distinguish between necessarily, if you intervene, then phi is true, which is the square brackets. And possibly, if you intervene on x, then phi is true, which are the diamond brackets on the bottom. So you can make all kinds of statements regarding interventions. And these can all be expressed using the causal model. Okay, so first, I'm going to do some notation. There's lots of notation here, and I might want to clean it up somehow because otherwise it's going to be very difficult to parse. But since this function fm can take on a varied domain, right? It's a generalized function. So the arguments are going to determine its domain. The codomain, strictly speaking, is always going to consist of all the exogenous variables and all the endogenous variables, but I might not be interested in all of them. I might be interested only in a subset, and so we can restrict the codomain. And I'm just going to assume that if I write y equals fm of xu, that just means I'm restricting the codomain to only those variables in y. I'm just going to ignore all the other ones. And now with that out of the way, I can make precise what it means that these generalized functions can capture all the statements in the causal language. Namely, the necessary interventions are captured by an equality sign, and the possible interventions, so stating that possibly it's the case that y equals y, can be captured by y being an element of the solution set for a particular input. Okay, so this is causal models as generalized functions. This is a detour because we were talking initially about abstractions, and where have they gone? Well, let's bring them back. And to do so, note that fm, it represents the entire causal model, but you can actually get each particular equation, so each function that appears in an equation, you can actually get that as simply a specific instantiation of fm. All you need to do is specify what the arguments are. So if you're considering a variable vi, then the function fi would take as arguments all the exogenous variables u and all the endogenous variables except for vi, right? That's the proper domain for that function. So if you just tell fm, those are the arguments I'm considering, it'll behave as fi. It'll be exactly the same thing. And that has to do with this idea where I mentioned if you give a variable to a function which is in the codomain, the function won't do anything to it. It'll just pass through the input. And therefore, if you have fm, which is this large composition of all these different functions, and you're giving it values for all the variables except vi, then all the other functions, so fj, fk, etc., they're all going to be just passing through values without doing anything. And that's why it'll only do something once you arrive at fi. There it'll compute, and that's it. Now, this is important because it means that we can now all of a sudden express the idea of marginalization in a very simple way. So marginalization is one particular type of abstraction. It essentially means I don't want to speak about certain variables anymore, so I'm just going to pretend that they don't exist. And other than that, the causal model stays the same. So say we only want to speak about the variables in S, where S is some subset of the endogenous variables. Well, to make that precise, you just get rid of all the other variables, you get rid of all their equations, and the remaining equations, you have to specify what they look like now. Well, you're going to do that by simply speaking about the arguments such that they only mention S. So you can define a weak reduction, which is essentially marginalization, by just taking a causal model, and for each variable, you're going to give as its equation fm, which is the generalized function for the entire causal model, but you're going to give it as its arguments only the variables in S and the exogenous variables, of course. Now, what is such a marginalization? It conceptually comes down to the idea that all the variables which are not in S, they haven't been observed, and also we assume that they are not intervened upon. They're just playing nice. We're just passing them through. We're not doing anything with them. So note in particular that the function fm is the composition of all the functions of our original model, also the functions of those variables that we've removed. So the variables are still somehow implicitly there in fm. Okay, this is a weak reduction, and I've expressed how we can, or I've shown you how we can express it. This is not very far removed from what we were looking at earlier. This is an example. I'm going to have to skip that. We had our abstractions, and I already showed you how I wanted to define it. I just hadn't explained what the symbols meant. So now I can at least make that precise, right? So this is what we had before, the definition. And I've explained now to you what fm is. So fmh is going to be the function for the high level, and flm is for the low level. So we've given meaning to that statement. And then for the canonical abstraction, I told you that the equation is just going to be such that we're going to restrict the arguments to those that are appropriate. And this is exactly the same idea as I just gave you for weak reduction. The only thing I've done is I've added the function tau as an intermediary. So you might see a weak reduction as simply where tau is the identity function. We're not doing anything with the variables anymore. We're just taking them as are. And abstraction just says, okay, fine. You might be getting rid of some variables, and the other variables, you're going to a different signature by the use of tau. But other than that, the idea still applies. You can write down its equation by specifying the appropriate arguments for that equation. And so this immediately gives you the construction of a high-level causal model. Again, an example which I'll go over because I just want to briefly say something about strong reductions. So fm takes into account all the equations, so all the functions that were present in the model. But at the end of the day, it's a composition of all those functions. And so there's an obvious generalization you might want to consider. What if I leave out some of the functions in this composition? I should be able to do that and still make sense of it. And indeed, we can generalize to fn, where n is just any subset of the endogenous variables. I'm now switching. It's no longer a vector notation because n used to stand for a network. Doesn't matter. It's just a subset of variables. And we can then consider the function, which is the composition of all the functions associated with those variables. And you have to make sure, again, as we did earlier, that the ordering of those functions is sensible so that you don't have a descendant which occurs before its ancestor, because that wouldn't make sense. But other than that, once you have n, you can specify the function fn. And we can then make sense of the fact that some tuple y is an element of the solutions to fn for a certain input x. In particular, if it's fully determined, that means that there's only one solution, right? So then y equals fn of x. And this is an idea of fully determining, meaning there's no indeterminism left. So the moment that you have x and all you need is the functions for n, then you already know what the values for y are. Now, interestingly, if that's true for some n, it's always also going to be true for the full causal model, for the full m, fm. So in this sense, considering a function fn and considering what relations of full determination this still allows, gives you a way of viewing this as a reduction, a strong reduction of the original model, so that some information, all the information about the full determination that we have is maintained. It's still there. It's just that it might have lost a lot of other interesting determination relations. So you're just becoming agnostic regarding a whole bunch of relations that were there in the original model. You don't know what they are anymore. But if you have a relation which is identifiable in the strong reduction, then it definitely also exists in the original model. Now, how to think of this? The variables that we're reducing away, we don't even assume knowledge about their existence. So with weak reduction, we assumed that they were just unobserved, but they were just being there and they were just still mediating all the influence. We weren't intervening. Here, the idea is we don't even know that they exist, and whether there's one variable or multiple, we also don't know whether they're being intervened upon or not. We're becoming agnostic regarding that, and then we're going to consider what the result is. So I define a strong reduction by simply considering a set of variables as before that you want to keep and getting rid of all the other variables. The difference here is that with weak reduction, we still made use of our FM. So the entire causal model, meaning that all the functions were still playing a part. With the strong reduction, we're just going to use the original equation for the variable, and we're going to restrict the arguments to the variables that we're still concerned with. This means that all the equations and all the functions for the variables that we've reduced away, they're gone. So they could be anything. And in fact, there could be multiple versions of one variable, and still all the statements that are true in the strong reduced model will hold as well in the, or at least stronger versions of those statements will hold in the original causal model. It's more determined statements.
Slender.
Yes, I'm
just yeah, not quite. But just flagging, maybe 3 or 4 minutes left, and I know Danya needs to go, and she's the one doing the recording. So we'll probably want to actually cut off right at 12.
Right, I'm actually almost finished. So this is strong reduction, and then the obvious idea would be we can combine this with an abstraction as well, and that's what I call the partial abstraction. I'm not giving you the definition because well, there's no need to spell it out. But I'm going to keep it at that. I've just laid out a whole bunch of different ways that we can use generalized functions, and some of those relate to abstractions, but I think there's also interest in these generalized functions independently of it. Here's an example of a strong reduction. Again, I won't go through it, but people can look at it afterwards, because I know that this went very quick and was very abstract, not intended. Another example to show you the difference between weak reduction and strong reduction. So in particular, we might have that common causes that were prevalent in a low-level causal model, we might forget that they exist. So we might lose causal sufficiency because we might not know anymore that 2 variables were had a common cause. And again, we can express everything about these strong reductions using generalized functions. Okay, now I'll just want to thank a bunch of people, because I've had lots of discussions already with people about this. But as I said, this is still very far from finished work. And I, of course, also want to thank the organizers and Yu Chen for giving comments on this very, very unprepared or unfinished work. Thanks a lot.